Hello, I'm Andrea Luppi from the University of Cambridge and the Montreal Neurological Institute, and I'll be presenting to you some work that I've been conducting across my PhD and postdoctoral appointments. So let's get started. The whole point of my PhD was to try and understand the neural mechanisms of human consciousness. But consciousness is a notoriously difficult phenomenon to pin down because, in the words of William James, it's like the flights and perchings of a bird. And so a lot of what we do is trying to make consciousness scientifically amenable to investigation so that we can avoid a situation like the one depicted in this slide here. But to do that, one way that we can make headway is by bridging the micro and the macro scales to understand how consciousness emerges as a biological phenomenon. And in particular, one excellent way that we can do that in terms of our ability to study the human brain is by using pharmacological agents, because those agents act at the microscale in terms of their molecular mechanisms of action, but eventually they can have profound implications for the macroscale, both in terms of cognition, but also in terms of brain activity. And in particular, here we focus on both. We choose drugs that have effects on large-scale brain activation, because we study them with functional MRI, but the ones that we select are those that profoundly affect consciousness, namely psychedelics, anaesthetics, and cognitive enhancers. So here is the outline of the first part of our work, which is we have 11 different drugs, 3 anesthetics, including both wakefulness and recovery comparison, and then 2 cognitive enhancers, and 6 different psychedelics, including ketamine, which at low doses acts as an atypical psychedelic. And we have functional resonant MRI scans of people both on the drug and on a placebo or before anesthesia. And we can then evaluate how different drugs change the overall functional connectivity of the brain, so the way that regions talk to each other. In addition to this, we also had access to a recently compiled database of PET maps pertaining to different receptor and transporter systems, which were put together from in vivo PET mapping by Justine Hansen in the group of Dr. Misic, where I'm now working as a postdoc. And what we can do then is, since we know that these drugs act through the receptors that are being shown here, we can map them onto each other to see whether these different drugs activate different kinds of receptors and how they do so. Specifically, the first relatively simple analysis that we can ask is there a similarity between which regions co-express different receptors and which regions are similarly affected by different drugs? And the answer is yes, because we can find a positive correlation between the two. But we want to go deeper than this, and to do so, we resort to multivariate analysis, namely partial least squares, which lets us find underlying latent variables that explain most of the covariance between, on the one hand, the patterns of functional connectivity change induced by the drugs, and on the other hand, the pattern of receptor and transporter expression. And in particular, we find that there are 2 principal latent variables that explain most of the covariance between those 2 patterns in a way that is significant against different null models. Namely, we find that there is one pattern that separates the top and the bottom of the brain, and a second principal pattern that separates the well-known unimodal transmodal axis of the brain. But in addition to doing so, it also separates anesthetics from psychedelics and cognitive enhancers on the one hand. And in terms of neurotransmitter systems, it separates receptors against transporters. And what we find is that, as expected, this principal axis is also well aligned with a number of different anatomical characterizations of the cortical hierarchy from different modalities, including functional MRI, as well as myelin content and principal components of both neurosynth co-activation, as well as gene expression and evolutionary expansion, which all map onto the same single gradient of drug receptor co-expression. In particular, though, we can also map these 2 systems onto each other, these 2 latent variables, so that we can develop a more comprehensive landscape of the way the different drugs act onto each of the different neurotransmitter systems. Because what we find is that there isn't a one-to-one mapping, as we might have accepted, but rather in terms of how these different drugs exert their actual effects on the brain and how they manifest in terms of functional connectivity, we find that each drug seems to activate a whole variety of different neurotransmitter systems, at least according to our model. So in addition to this, we can also find that pharmacological co-susceptibility, so the way the different regions are similarly affected by different drugs, also recapitulates the way that these regions are similarly affected by different diseases and disorders in terms of the cortical thickness abnormality that we have obtained here from the Enigma Toolbox database. Which means that, in other words, if regions are similarly affected by drugs, they're also similarly affected by disorders. So potentially, there is a way to act on regions that are susceptible to different disorders by finding which drugs would be most helpful in rebalancing the activity and the connectivity of those regions. Now, of course, all of this was based on correlation, and we know that we want to go deeper than that. And for this, I suggest that you come to my other posters, which are using different, more mechanistic frameworks, namely network control energy, but also dynamic mean field modeling, to try and understand how different drugs and different mechanisms can act on the way that functional activity and connectivity are organized. So overall, what I hope I can convince you of is that we can start mapping the effects of different drugs onto the expression of different receptor systems, and hope that we can obtain a compass to the effect of different drugs. Of course, this work, you can find a lot more about it in a recent publication in Science Advances, and you can scan the QR code to be taken directly to that publication. And this was an effort that included many countries and many different collaborators. And I want to emphasize in particular those who contributed the data that otherwise would not have been possible without their key help. And finally, thank you all for your attention, and I'll be happy to take any questions that you have.